Hello everyone, my name is Prashant Sharma, and this presentation is on the stability of dynamic systems. The order of a dynamic system equals the number of state variables. For example, as shown on slide 2, a first-order dynamic system has one method of storing energy. A third-order system has at least 3 different methods of storing energy. And an nth-order system has at least n different methods of storing energy. Consider the system x dot vector equals A matrix times x vector plus B matrix times the input variable. This equation is shown on slide 3. Now assume the input is 0. What happens to the system when there is no input? We will analyze this during the rest of this presentation. On slide 4, consider an example with a mass and a damper. The only stated variable, x1, is velocity. Using Newton's second law, this state variable leads to the state equation x1 dot equals negative c over m times x1 plus 1 over m times u1. We will assume that there is no input force, which causes a second set of terms to equal 0. Now, we are left with x1 dot equals negative c over m times x1. Now, assume x1 of t equals a e to the lambda times time. The derivative, which is also the acceleration, of this function will be x1 dot equals lambda times a times e to the lambda times time, which can be reduced to x1 dot equals lambda times x1. Comparing this equation to the one on the slide before, we can conclude that lambda equals negative c over m. Plugging this function back into the original equation, we now have x1 of t equals A matrix times e to the negative c over m times time. Setting t equal to 0 seconds allows us to conclude that x1 of 0 equals a. Substituting this answer into the equation, we finally obtain x1 of t equals x1 of 0 times e to the negative c over m times time. Now we begin to analyze the behavior of the system by observing the function's behavior to the graphs on this slide. When lambda is negative, the system is considered to be stable and causes the exponential curve to approach 0 over a certain period of time. However, if lambda is positive, the system is considered unstable and causes the curve to increase exponentially. The magnitude of lambda determines how quickly the function will grow or decay. For example, if c increases or m decreases for a positive lambda, the system's response will increase much faster than if the c and m remained constant. Similarly, if c decreases or m increases, the system will reach equilibrium much quicker than if c and m remain the same. Graphs 10 and 11 show a sinusoidally unstable system, whereas graphs 9 and 12 show a sinusoidally stable system. Graph 1 is considered marginally stable. This means that if a system is perturbed, the system's dynamics will neither increase nor decrease, but instead remain the same, thereby producing a flat response. The takeaways from the graphs are that when lambda is less than 0, the system is stable. When lambda equals to 0, the system is marginally stable. And when lambda is greater than 0, the system is unstable. Matt and Josh will now discuss the behavior of a system that includes a mass, a damper, and a spring.
We are going to be looking at a mass spring damper problem and trying to determine what the response would be given initial conditions and no input. Basically, if we set the mass in motion, we want to know how it's going to react. This can be done with the help of eigenvalues and eigenvectors, which we'll be working through shortly. Here we have a mass spring damper system with spring constant K, damping coefficient C, and input force U1 acting on the mass. The spring and damper are connected to the mass and to the ground. For this example, we have two state variables. X1 is defined as the position of the mass, m. X2 is defined as the velocity of m. Looking at our system, we have two state equations. They are x1 dot equals x2, and x2 dot, using sum of the forces, equals negative k over m x2 minus c over m x2 plus u1 over m. At this point, we now need to linearize our system. So we'll start with x dot equals our matrix 0, 1, negative k over m, and negative c over m, plus 0, 1 over m, u1. Alright, so at this point we're going to eliminate the u1 variable because this problem is basically just the mass is in motion and we're not going to keep a force on it the entire time. So at this point we need to linearize our system, but before we do that we need to make some assumptions in doing so. So I'll erase this part and we'll continue on. Alright, so first thing we need to assume is that x at time 0 equals x naught. We also assume that x equals x naught e to the lambda t. It's the response of a system like this. X dot then equals lambda x naught e to lambda t, and through substitution we then find that x dot equals lambda x. From before we know what the matrix value for x dot is, so we then set them equal to each other. So now we have lambda x equals the matrix 0, 1, negative k over m, negative c over m, x. We can break apart our variables into x1 and x2 to make it easier to solve, so we'll do that next. At this point, we need to solve our matrix equation. So to do that, simply multiply the column by the row. So that leaves us with, for the first line, x2 equals lambda x1. And for the second line, negative k over m x1 minus c over m x2 equals lambda x2. By substitution, we'll take lambda x1 and plug it in many times in x2. That leaves us with negative k over m x1 minus c over m lambda x1 equals lambda squared x1. Since there's an x1 in each part of the equation, we can eliminate that. And what we'll do is we'll put it in matrix or quadratic form. This is with lambda squared plus c over m lambda plus k over m equals 0. At this point, all we need to do is solve for the quadratic equation for lambda, and that will give us our eigenvalue. So that's about it. What we just did is the result of this problem is that given an initial condition, we are able to mathematically represent the free response to the mass spring damper system. In this case, the system will operate at some frequency that we paired by a decreasing sinusoidal function.